In today's lesson, we are going to be looking at scatter plots and regressions with Desmos. So in our last lesson, we looked at scatter plots, we looked at creating a line of best fit or a trend line, and we also mentioned it as another term, a linear regression. So we're doing the same thing today, except instead of using kind of our own perception or what we think or where we think the line of best fit should go, we're going to be using technology to create the line for us to make sure it's accurate, and we'll see why later on at the end of the lesson. So biologists, chemists, engineers, sociologists, and businesses all rely on mathematical modeling to better understand the relationships they study. Often the data does not form a linear relationship, and we must use a different type of model. Now, in all the examples we will be looking at, they will be forming a linear relationship or have a linear relationship. And then the term regression, which we've brought up before, refers to a technique of finding a mathematical model that best fits a set of data. We will be focusing on determining the equation of a line of best fit called a linear regression. So like we just said, all of the relationships we look at will be a linear relationship, therefore we will be creating a linear regression, which basically just means a line of best fit. Because again, if we want a line of best fit, we want to use it to make predictions or to model a scenario or a relationship that we've found. And we've done this by hand, but now we're going to look at using technology. So a researcher is studying the growth pattern of trees as part of a forest management project. A sample of trees yields the following relationship between age and diameter of a species of oak tree. So we see the table here, the age and diameter are X and our Y values, and we see a scatter plot that has been made. Now we're going to go through and do the same thing. We are going to create a scatter plot using technology, specifically Desmos. So if you open up another browser or another tab and you type desmos.com, it will take you to this page. All we really need is to click on the graphing calculator part. We don't need to do anything fancy. We don't need to log in. Now, if you do want to log in, there is an option to do that, and it would just let you save your worksheets. But again, for this case, you don't really need to. So what we're going to do, we can see the instructions kind of up in the box, and again, we'll walk through it, but you should have the instructions on the handout as well. So we are going to click the plus sign up at the top, says add item, and we're going to go down to a table. Now we're not going to adjust anything in the table, we're not going to add any new titles, we're going to keep it X1 and Y1, and we're just going to go through and enter all of the data exactly as we see it. So I'm going to scroll back up. So again, 5, 8, 12, 17, 20, 22, 28, 33, 35, 36, 40, and then 47, 37, 52, 34, 52, 21, 18, 17, 10, 9, 5. So I've just basically entered the table or entered the data as I saw it in my table, which is again exactly what we do in step 2. And we should start to see that as we're doing that, we start to get a few points. We see one point here, which is our 5 point. Oh, can't really see it. We move this down. We see our 5 point, but we don't really see anything else. So now if we go up to the graph settings, maybe there was an option somewhere. Oh, the plus sign over here. So over on underneath the table, if we see this plus sign, it says zoom fit. If we click that, it zooms out and lets us see all of our data. So this is our scatter plot. We can see as well, if we scroll back in our notes or the handout, we can see that it does match the graph that we have here. So we've just recreated that. So great, easy way to recreate our data or create our scatter plot, but again, that wasn't necessarily the hard part. It does make it nice and neat, But the main thing that we use the technology for is the linear regression, or the equation, which creates the line of best fit. Based on our previous lesson, we would do our best to draw a line that would match the steepness, match the direction, and try to minimize the distance between or from the line and the points. By using technology, it automatically creates the best one of those lines for us, or it creates the best line of best fit, or the correct line of best fit. So it takes out that guesswork that we talked about in the previous lesson. So how we're going to do that is we are going to, in the next line, where we see number 2, we're just going to click to enter in a new function, and we're going to type out specifically y1. So it automatically created a subscript. I didn't do anything fancy. If you could see my typing, I just press Y and I just press 1. It automatically makes it a subscript. I'm going to use this little squiggly line, or a tilde as they call it, which is basically going to tell Desmos to create a regression, or come up with a line of best fit. You should find it next to the 1 on your keyboard. You probably have to hold Shift and press the button. Then we're going to do A x1. Again, it will automatically subscript it. So right now we can see that it's created a line of best fit already. However, we should remember that our equation of a line is just not y equals mx. There is a constant. If we don't put the plus b, it would always create a line that would go through the point 0, 0 as our y-intercept. But as we've talked about previously, you can have a constant in your equation or in your model. So we want to make sure that Desmos understands that we're allowed a constant. So once we type that formula in, we see a bunch of things pop up already. So this is automatically generated. We don't have to do anything. So if we go back, I'm going to type in the formula again, and you can see that those values pop up automatically. There's nothing that we do to get those values. It creates them for us right away. So what this does is it creates an equation, or a line of best fit, in the form y equals mx plus b. And it does tell us our a and our b value, or based off of our equation, our m and our b. So again, Desmos just requires different variables when we're entering it, but a represents the multiplier. We should be able to see that by where it's located in the equation, and b is our constant at the end. So if we go back to our graph, or our note, we can, same equation that we got. If we really wanted to, we could modify the colors or whatnot. And you see, we just click and hold, and it lets us change the color. Same thing if we want it to go away or not. We can also click up on the green. Again, we can change the colors. We could change what the mark looks like, and so on. So with our line of best fit, again, we've created it. We have our scatter plot, our line, or linear regression. And specifically, we're going to focus on this part now, this little box that comes up. Because what this does is it gives us the regression equation, or basically the equation of that line. And again, all we had to do, we typed in the equation, essentially y equals a x plus b. The a and the b value we have to take from what Desmos spits out and put it into our equation, or substitute it in. The two other values, the r squared and the r value, they just tell us how strong our relationship is. Basically, the higher the value is, or the closer it is to 1, the stronger it will be. Whether it's positive or negative is okay. We're just looking for how close to 1, whether it's positive or negative, is it. So closer to positive or negative 1, the stronger. So just if you want to add in that little extra piece of information, just to get a better understanding. So kind of zoomed in here, but we should see that our r squared and our r value are 0.96 and 0.98 respectively, which means we have a very strong relationship. And if we go back and look at our graph, we should be able to see that the points, or the points of our scatter plot are very, very close to the line. So again, that means that our line indicates a very strong relationship. What we can use that line for now, because we have a specific equation, rather than make an estimation by drawing a line up to our line from one axis and then over to the other, we can use the actual equation. So we can use the actual y equals 1.096 x minus 1.6. Let me just scroll back up to make sure we got the correct one. 1.687. You will have more decimals in Desmos, so again, if you need to round it to 2 decimal places, that's fine as well. Here we've rounded to 3. So we can use this equation to get an accurate prediction rather than, like we said before, just drawing the line up and assuming that our line is correct. Now, there's a couple things we need to do or understand in order to use this equation. Because we don't have a scenario, or because it is a different scenario, we need to make sure that we understand what does the y and what do the x variables represent. So what does x equal and what does y equal? And again, you may not remember, but if you go back all the way back to our table, remember we said the first column is usually the x, the second one is the y. So in this case, our age is our x value and our diameter is the y value. So we have our age and our diameter. And this is important because we will be given some of this information. So we need to know what to substitute in. So if we look at our equation, or our scenario, use the regression equation to predict the diameter of a tree whose age is 50 years old. That's the key information. And that tells us, if we move this down a little bit, that tells us that x equals 50, and we need to find the diameter. So in our equation, all we have to do is sub in x, 50 for x. So y equals 1.096 times 50 minus 1.687, and this just becomes one calculation. And we should get y equals 53.113. So therefore the diameter we'd say the diameter would be 53.113 centimeters. Now that's one way we can use the equation. We saw in the previous lesson that there is another way by looking at the other variable or being given the other variable. So again, same idea, use the regression equation to predict the age of a tree whose diameter is 85. So again, remembering that x is the age, y is the diameter, and our equation was y equals, I already forgot that, 1.096 x minus 1.687. Now the other scenario is that we plug in a different value, or a value for a different variable, because now we're told what the diameter is. So this is telling us that y equals 85 now. So in our equation, we're going to replace the y with 85. So 85 equals 1.096 x minus 1.687. And now this is a two-step equation. So we have solved equations like this in the past, in our previous lessons. So if you do need a refresher, please go back and look at those or at that unit. So what we're going to do first is move over the separate term. So 1.687 is going to move over. It's going to be plus. So plus 1.687 on both sides. One side will cancel out. We get 86.687 equals 1.096x. Divide both sides by 1.096. One side will cancel out. And when we divide, we end up with 79.1 equals x. So therefore, the tree is 79.1 years old. So again, the main thing is just how we can use technology to create an accurate line of best fit and give us a specific equation. Again, the reason why we want this specific equation is so that we can make accurate predictions using our substitution and solving equations techniques that we've looked at before. This way, everyone should be getting the same answer. A prediction or a model really only helps if everyone is getting the same information. Right? So in our previous lesson, when we did this by hand, everyone was kind of getting in the same ballpark. But here, when we use technology, when we use the equation, everyone should get the same answer, provided they solve the equation correctly, which again, there are right and wrong ways. Or there is only really one right way or one right answer to get once you solve it. So again, just make sure you can follow those steps to create an equation, or to create a scatter plot and then a linear regression, and then understand how to use that equation to make predictions.